Hello everyone, see you again for the next video. Chapter 8, counters. We done chapter 7 of the flip-flop. Now we move on to the chapter 8, counters. Counters is a device for counting numbers in up or down sequence. Counter up or counter down. Up counter, counter numbers in up sequence. Down counter, counter number in down sequence. 0, 1, 2, 3, 4, 5, 6. 6, 5, 4, 3, 2, 1, 0. So that is down counter. As you know, the binary count sequence follows a familiar pattern of zeros and 1. So this is the sequence of counter. LSB change on every number. The next big change on every 2 number. The next big change on every 4 number. So this is the counter, okay, of pattern of zeros and 1. A counter can form the same pattern of zeros and ones with logic level. The first stage in the counter represent the least significant bit. The first stage in the counter, least significant bit. Notice that these waveforms follow the same pattern as counting in binary. So this is the waveform. The counter is always looking at the bottom value is the MSB 0, 0, 0, 0, 0, 1, 0, 1, 0. Okay, 0, 1, 1. Not start from the upper first, 0, 0, 0. If this one is wrong, this is not the up or down counter. It must start from here. Okay, 0, 0, 0, the waveform. One of the most widely application of JK flip-flop is counter. So counter ni normally we use JK flip-flop. We have SR, we have also D. But normally JK is widely used for the counters. There are two types of in designing binary counter: asynchronous counter, synchronous counter. Non-synchronous, synchronous, asynchronous, synchronous. Both counters are different in terms of their design, but their function is similar. Design is different, tapi the function is for counter, for counting. Asynchronous not occurring at the same time. Bukan berlaku pada satu masa. An asynchronous counter is one in which the flip-flop within the counter do not change states at exactly the same time because they do not have a common clock path. So the keyword here is they do not have a common clock path. So kalau tak ada clock path means that the counter is asynchronous counter which is not occurring at the same time. Recall that there are two types of JK, positive and negative edge trigger. Both of them will have slightly different connection in order to become an asynchronous counter. We will examine the connection of 3-bit asynchronous counter for both flip-flops, PET and NET. So this is the example of 3-bit asynchronous counter using positive edge trigger JK flip-flop. How do you know this circuit is positive? Because there is no bubble at the input clock. If there is a bubble, so it is a NET or negative JK flip-flop. So the pulse clock is only feed to the first flip-flop, only feed to the first. Then the next is waiting. The next clock is waiting from the first flip-flop. When using PET JK flip-flop, output Q bar is connected as the next flip-flop. Kalau dia positif, clock ni datang daripada sini. Kalau clock ni datang daripada sini, ada sebab. We will see why. What is the reason we connect the clock of second flip-flop and third flip-flop to the output Q bar. We will see. Recall that for PET-JK flip-flop, when both input J equals to 1, J equals to K equals to 1, the output will be toggle at positive H clock. Toggle. J sama dengan 1, K sama dengan 1, the output will be toggle. You refer to the stable of JK flip-flop. That is what happened when the first flip-flop. That is what happened for the first flip-flop. This toggle action will be the clock for the next flip-flop. As for that, the next flip-flop toggle output will be 2 times slower than the original clock. By continuing this kind of connection, the next flip-flop output will become 1 time slower than the previous flip-flop output. We will see what is the effect when we connect the second flip-flop to the output Q bar. Q0 will be the counter's LSB, while Q2 is the MSB. So this is LSB, this is MSB. And as for that, the counter will count 0, 0, 0, 0. This first one 0, 0, 0. Second one 0, 0, 1, 0, 1, 0, so on and so forth. Okay. How to get this output? You refer to the this one. Okay. When using negative JK flip-flop, the only difference is the connection of previous for output Q. The next flip-flop is clock. Presentnya hanya pada Q ni. Q ni, yang tadi Q bar, now Q is become input to the clock of the next flip-flop. So this is the output dia lah. Kan? Notice that all flip-flop are triggered on negative H. Negative H. Kosong. Kan? 1, 1. 1, 1, 1. This is the, look at 1, 1, 1. Kan? 0, 0, 0. 0, 0, 1. 0, 1, 0, seterusnya dan seterusnya. Okay? Try to understand this one by looking at the chapter 7, the details of the flip-flop. So this asynchronous is actually continuing the previous chapter 7 of the flip-flop. Propagation delay. Asynchronous counters are sometimes called ripple counters because the stages do not all change together. For certain application requiring high clock rates, this is a major advantages. Notice how delay are cumulative, as such stage in a counter is clocked later than the previous stage. So this trigger ni is actually having a delay. It's not serentak macam ni kan, dia ada delay. Dia ada delay sikit lah. So delay ni kita tengok T time delay PLH. Time propagation dia nak pergi low to high. Dia nak naik low to high tu dia ada time sikit. Walaupun actually kita lukis at the same time kan, sama dengan clock ni, tapi sebenarnya dia ada, bila clock ada, dia ada sedikit delay. Okay, TPHL positive high to low. Alright, time high, low to high. Clock to Q0, Q0 to Q1. So if you look at here, PHL ada PLH. So ada basically the waveform ni akan ada we call it propagation delay. As discussed earlier, each binary bit can only count up to numbers following the sequence of 2 power of X, which is X, 2, 4, 8, 16, 32. Kalau kita ada satu flip-flop, kita boleh count 0, 1. Kalau kita ada dua flip-flop, which is 4, 2 power of 4, kita boleh count 0, 1, 2, 3. 0, 0, 0, 1, 1, 0, 1, 1. However, we normally count in decimal, which is in the sequence of 10 power of x. For this purpose, the synchronous counter that we have constructed needs to be modified by limiting the count up to 10 only. After that, it needs to be reset back to 0. Kan? First, we need to construct a 4-bit asynchronous counter as it can count from 0 to 15. Then we limit the count at 10 by adding the NAND gate. Recall back that usage of clear where it forces the output to become 0. This is how all flip-flop will be reset back to 0. So kalau kita nak count nombor, for example, if you use 3 flip-flop, to power of 3, kan? To power of 3 is 8. So dia count 0 to 7. Tapi kita counter kita tu, we want to count only 0 to 5. Dah tak boleh, kan? That's why we need to have a NAND gate ni, so that we can limit the count. For example, kita ada 4 bit. So 4 bit to power of 4 supposed to be 16. So dia count antara 000 to 1111. But we want our counter to count from 0 to 10 only. So we need to add NAND gate so that it can reset at 10 by using CLR. Okay. So this is the example of asynchronous counter, tapi dia count only at a certain number. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, dah reset. Kalau kita tak reset, it will count 0 to 15. So the way to reset is to put the NAND gate. Look at the NAND gate tu kat sini. Look at the NAND gate. Kan? So kita ada the output from NAND gate we goes to the reset tu. So dia akan reset. Dia akan reset kat situ. Okay. So this is the example. So if you look at this carefully, this input of NAND gate is coming from Q1. This and Q2. So bila kita tengok perhati dekat sini, our preset ni, kita ada bubble dekat situ, means that the preset, the clear or preset ni, it require logic 0, kan? Logic 0 in order to reset all output of flip-flop to become 0. Same goes to here. This connected to Q1 and Q3. Q1 and Q3 for this is for PET positive, this is for negative H trigger. Output of synchronous decade counter using PET, if you look at this carefully, dia akan reset dekat mana tu? Dia akan reset dekat kita nak kena dapat output ni kejap dia akan reset dekat this is the clock Q0, 1, 2, 3, Q0, Q1, Q2, Q3, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1. So dia akan reset dekat sini. Ni dekat sini. Tak reset dekat sini kan. Dekat sini ni. Ni 1, 0, 0, 1, 0, 0, 1. 1, 0, 0, 1. Terus dan kemudian dia akan reset to 0. So 1, 0, 0, 1. Q0 is 1. Kalau kita perhatikan yang ni, dia connect to Q1 kan. Q1 means that Q3, Q2, Q1, Q0, Q1 and Q3, Q1 and Q3. 1, 0, 1, 0, 1. 0, 1. If here is 0, here is 1, means that the output is 1. So, bila output 1, dia akan reset lah. Kalau 0, 0, 0, 1, 1, 0, sorry, 1, 1, 1, 1, 1, 1, 0. So, dia reset dekat 1, 1 kan. Dia nak naik dekat sini ni. Dia naik, terus dia reset. Okay. So, this is the place where the counter reset. Ni kat sini. So what is the input for the counter, this counter reset? The input must be Q1 equals to 1, Q3 equals to 1. Kalau 1, 1, ini dapat kosong kan. Kosong, dia akan reset the JK flip-flop. So sama juga dengan sini. So dalam case ni, dia akan reset apabila kita akan dapat, dia akan reset apabila kan ni, dia akan reset dekat 1, 1, 1, 0, 1. Betul tak? 1, 1, 0, 1. Dia akan reset dekat 1, 0, sorry, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1. 1, 0, dia akan reset dekat 1, 0, sini bukan ni, 0, 1, 1. Oh sorry, 1, 1, dia akan reset dekat 1, 0, 1, 1. 1, 0, 1, 1. 1, 0, 1, 1. 1, 0, sorry. 1, 0, Q1. 1, 0. Berapa tadi yang first tadi ya? Let me dia akan reset dekat 1, 0, 1, 1. 1, sorry, 1, 0, 1, 1. Oh, betul. Ini saja. Dia akan reset kat sini. So, dia punya counting dia 1, 0, 0, 1. 9, kosong ke 9. 10 kat sini ya. Terus dia reset. Okay. So this is the timing waveform. Beside from counting to 0, 0 to 9 kan, to 0, we can also count up to a certain number that we desire. Apply the same modification to the original asynchronous counter with the non-inputs are the number desired in binary form. As an example, for the modulus 12. 12 0 to 11 kan. 8, 4. As an example, for a modulus 12, asynchronous counter, the counter need to be reset at 12. Kan, need to be reset at 12. Yang ni need to be reset at 10. Tengok kita tengok. Yang need to be reset at 10 tadi. Ni kan 0, sini 0, 0, 0, 0, 0, sorry, 0, 0, 0, 1. Sampai dekat 10 kan. 1 0 0 1 9 kan, 0 hingga 9. Bila dia nak naik 10 je, 0 dia nak naik je 0 1 dia supposed to be 1 0 0 1 kan. Kemudian dia akan reset dekat 1 0 1 0. Bila dia jumpa 1 0 1 0 je, dia reset. Dia akan jadi, dia turun jadi 0 0 0 0. Jadi nombor yang akan kita kira 0 1 2 3 4 5 6 7 8 9. 10 dia tak kira. 9 dia nak naik 10 je, dia reset jadi 0 0 0 0. So kalau kita pergi ke mode 12 ni, reset at 1 1 0 0. Dia reset dekat ni 1 1 0 0. Kita tahu cara kita nak reset. Kalau kita nak buat modulus 12 ni, modulus 12 ni dia akan count 0 to 11 kan. Dia ada 12. 0 sampai 9 dia ada 12 number. 12 bit. 12 state. So, apa nombor 12? 1100. Jadi kita nak reset nombor dekat nombor 12 ni. So, kita tengok satu-satu ni. Satu-satu. So, ni Q. Ni cara dia. Q 3. Ni Q 2. This one Q 1. This one Q 0. So, kita tengok yang satu-satu ni tadi. So, satu-satu tu yang kita connected to AND gate. Apa yang satu, logik satu-satu? Q3 and Q2. So, connect. Q3 ni kena nampak. Q3. Kemudian, mana Q2? Ni Q2. This Q2 kan. Sorry. Q3 and Q berapa ni? Q3 naik sini. Q2 sini. Sini ke mana? Satu-satu. Kalau satu-satu kita akan dapat satu-satu kita akan dapat kosong. Kosong dia pergi reset lah. Same goes to this one tadi kan. Ini Q3 and Q1. Q3 and Q1 sebab kita reset dekat ni Q3 and Q3, Q2, Q1, Q0. Dalam kes ni Q3, Q2, Q1, so Q3 and Q2. Ini connected ke sini ni. This one is connected to here. Then dia reset dekat 1100. Okay. Then you can look at the asynchronous counter for yang ni tadi lah, for waveform ni, for that one. So this is the IC for asynchronous counter 74LS93A. Has one independent toggle JK flip-flop driven by clock A and 3 toggle JK flip-flop that form a synchronous counter driven by clock B. The counter can be extended to form a 4-bit counter by connecting Q0 to the CLKB input. So the two inputs are provided that clear the count. All JK and JK input are connected to internally. So this is the 4-bit. If you want to reset at what number, so you just connect this NAND gate to the output of the gate. Q output of the gate kan, Q0 ke Q1 ke Q2 ke Q3. So this is the 74LS39A connected as a modular 16 counter, connected as a decade counter. 12 modulate as a 12 counter. Okay, so that's all the asynchronous counter. I stop here. I will continue to the next video, chapter 8, part 2. Okay, thank you very much. See you in next video. Bye bye.